This is the solution to the problem flip string to monotone increasing. The goal is very simple: to count the number of bits to be flipped. You're given a particular string and you have to flip some particular bits in such a way that it takes the minimum amount of flips to get to a monotonically increasing string. Now, we define monotonically increasing string in this way. There are a couple of zeros towards the starting and a couple of 1 towards the ending. Now, they could be A zeros and B ones, mathematically speaking, and they could range from 0 to the length of S, which means that the entire string could be just zeros or the entire string could be just ones. Both of these are valid cases as well. However, the more generic representation is a couple of zeros here and a couple of ones here. Now, I want to focus on this particular point, the point at which we can break both of these apart. Now this point is very interesting because anything to the left of it is going to be a 0. That is how we define it. And anything to the right of it is going to be 1. Again, that is how we define it. We can make use of this very beautifully. But first, let's look at an example. In this case, you have 5 digits, 5 bits, 0, 0, 1, 1, and 0. Okay, this is mostly a visual representation and I'll explain what this means. First, let's talk about the trivial cases. A couple of zeros and a couple of ones. All the ones, all the zeros. So one of the cases says that convert all of these zeros to ones, which means that this, and this would be converted to 1, taking a cost of 3. The other thing says, hey, convert all of these to zeros. Basically 0 here and 0 here. So it takes the cost of 2. But it obviously begs the question that we could do better, couldn't we? See, we're starting from 0 here and we're going from 1 up till here, right? The goal is to find the breaking point. A breaking point says that anything to the left of it is zeros, anything to the right of it is ones. Now, if you found the most optimal breaking point, the only thing needed to be done is converting all of these zeros here to ones and all of ones in here to zeros. And that is the entire solution. Okay, let me walk you through what's happening in this case and we'll understand how we actually got to this breaking point. So the goal for this particular sequence of zeros, this trivial case, is convert every single one you see to a 0. And so red represents the cost taken. Initially it's 0. You encounter a 0, it's still 0. There is no cost for a 0. Again 0, no cost taken. If you see a 1, convert it to a 0, please. Flip it and we'll encounter a cost of total 1, as you can see at this level here. You'll again see another 1 here, so the cost jumps up to 2. And that is where you end with a 0 at the end, so no other cost has been taken. Cool. Now let's go towards the reverse side. Let's try to convert this particular string of bits to all ones. We'll start from 0 here as the total cost. At this point, 0 says that, okay, it has to be converted to 1 because we want all ones. So it encounters a cost of 1. It looks at 1, no cost taken. It looks at another one, no cost taken. It looks at 0 here and takes another piece of cost and looks at 0 here, another piece of cost. This should be above here. Like so. Yeah, cool. Now, why did we discuss this? See, because at each point of time, you can imagine sort of zeros fighting to make everything 0 and ones fighting to make everything 1. And at one particular time, which is going to be the breaking point of time, which is the breaking point, their total cost encountered would be the minimum possible. In fact, look at the green pieces here. From 0 to 0, if you were to consider the purple one, it gives a cost of 2. However, the red one gives a cost of 0. So the total is the cost of, it should be the cost of 2 here. Okay, let's fix this. We'll fix it later, fine. One note is messing up. Cool. Okay, from this guy to this guy, the purple says it's a cost of 1 and the red says it's a cost of 0. So the total cost is 1. Similarly, we'll figure it out for each and every single one of these intervals. At the end, you will find a particular point having the minimum cost as possible. And that is what the question asks you. It asks you to find the minimum number of flips. At this particular breaking point, what do you see? The cost and the level here are the same. It is at the level 1 because the total cost encountered is 1. The total cost of making all of these guys zeros and making all of these guys ones. Now it should make sense. And the cost is 1 because there is only this 0 to be converted to 1, and it would be the answer. To make things a bit more clear, let's look at a more complicated example of 1 0 1 0 1 1 0. Okay, now what's happening? In this case, we'll look at red again, which is the cost of converting ones to zeros, because we want everything to be 0. Red pushes for everything to be 0, and the purple pushes in the opposite direction. Green again represents their total costs. In this case, what do you observe? There are two particular points where the cost is 2. What does that mean? There are two possible answers. Obviously, the actual answer that we return is going to be 2, but in our mind, it should be more clear. So this could be one particular breaking point where everything to the left of it is 0 and everything to the right of it is 1. Now, how many zeros do you see here? 2 zeros, right? And that is the cost you see there. Make sense? Let's also consider this breaking point. It says that anything and everything to the left of it is zeros. So this one takes a cost of 1. Anything to the right of it is going to be all ones. So this 0 again takes a cost of 1, giving a total of 2, which is also the minimum. And now I think it should be more crystal clear about the exact logic what we are going to follow. Now there's one last implementation detail that's left. See, it's okay to consider this way or this way, but the goal is to actually consider each and every single index. The goal is to find a breaking point. And so we'll actually, just for the sake of convenience, start from the index 0 here. At this point of time, the red ones are going fine, but the purple ones are going in the opposite direction. Converting zeros to 1 is going in the opposite direction, right? So let's just flip it again. And that is how we'll consider it in the implementation. Let's actually look at it. First, we'll get the length of the particular string. And then I'll say flipped zeros. Because there are number of zeros already flipped because of this guy. Because we are going in the reverse. So the flipped zeros would be actually equal to the count of 0. These are the zeros that have been already flipped because we are going in the opposite direction. Only for this guy though. For flipped, or actually ones to be flipped, which I'll call ones to zeros, we'll start off with 0 as usual. Now again, we want to initialize the final answer as well. So let's call result as number of flipped zeros. That is a valid starting point, the worst possible case where everything is from this index. And what does this index suggest? Everything is ones. Okay, it should make more sense once we type out the entire thing. We'll iterate over each character in the string. And this is where things will get a bit tricky. Bear with me. We'll say flipped zeros has to be updated to something, and ones to zeros has to be updated to something as well. Now, because we're going in this direction, the number of ones to be zeros converted are going to increase. We'll say C equals to the count 1. We're basically saying, okay, if there is a 1, convert it to a 0. Why do we want to convert it to a 0? Because the breaking point has shifted. At every iteration, the breaking point shifts by 1. So every 1 towards this side has to be converted to a 0, and that's why the cost increases. At the same time, the cost of this now will decrease because of the exact opposite reasons, or the exact same reasons since we are considering it in reverse. At the end, what do you want? You want the result to be same min of result and flipped zeros. The total cost, flipped zeros plus ones to zeros. Cool. At the end, return result. Cool. Let's do a quick sanity check. Cool, works on the first try. Let's submit this and we'll walk through the space and time complexities. Great, works. Okay, so the space and time complexity, this is order of one operation for both space and time. Flipped zeros counts the number of zeros in the string, so it takes order of n and will store it in a single variable, order of one space. This again, same order of one for both space time, order of one both space time. This entire loop will now take order of n and time. And what's the space? These flipped zeros, ones to zeros, and results are three variables. So a total of order of three, which is order of one space complexity. Basically meaning order of n time complexity and order of one space complexity. Cool. And yeah, this is it for the solution of flip string to monotone increasing. There's a more verbose sort of explanation of what's going on as well, an intuitive and visual explanation in my writer. I'll put the link in the description below. Anyways, as usual, if you have any feedback, if you like this video, please make sure to comment or at least give a like. And yeah, that's it. If you have any more questions, by the way, feel free to post them in the comment section below. Cool. Bye bye.